Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. In this lecture, we simply continue the discussion which we started in the previous lecture on the turbulence in fluids. Okay. In the previous lecture, we started by saying you different elements or piece of elements by which we can try to approach the problem of turbulence. Okay. So because of the non-linearity and very high irregularity, as you can easily understand that a normal very easy analytical treatment for turbulence is not possible. And then there came the suggestion by Taylor in the year 1935, who said that we should not be interested in the one-point quantities. Rather, we should be interested in the study in the study of the two-point correlation functions of velocity, pressure, for example, and their evolution. And then following that, von Karman and Howard in the year 1938, they studied that and they obtained analytical relations for those correlation functions in the year 1938 for homogeneous and isotropic turbulence. Okay. Now, I did not present the exact analytical results by von Karman and Howard because they are really a bit technically non-trivial. So just I said that just take it as an information that they did it, and actually the next piece was done by Kolmogorov in the year 1941, and that is the so-called the first exact relation in turbulence. So that I will talk a bit about, really a bit in this discussion. But in this discussion, we will start by discussing the heuristic phenomenological approach to turbulence, which was initiated by Richardson in the year 1921. So what I am just trying to say is that historically the style of attacking the problem of turbulence was not very much mathematically very rigorous, but Richardson, who was an expert in the weather department, so he was basically much more interested in modeling the atmospheric turbulence, and he observed that a turbulent field always mostly consists of eddies or vortex-like structures of different sizes. Okay. And then he proposed his picture of Richardson cascade, and it was merged with different hypotheses of Kolmogorov. Okay, so they are called the Kolmogorov's assumptions of universal equilibrium. Okay, or Kolmogorov's universality hypothesis, Kolmogorov's okay. So there are several names of that. I am not going into the detail of all these hypotheses step by step and the Richardson cascade separately, but here what I will try to tell you the combined picture and the net picture of all these things. So if you can compile all this Richardson cascade image and the Kolmogorov along with the Kolmogorov hypothesis, what you will get is the following. So the turbulent velocity field is thought to be composed of eddies of different sizes. Okay. The energy by the forcing term, if you remember, so this is the forcing term by which energy is injected into the system. Okay. That can be of course some body force or some random force. Okay. So whether just by a regular body force like gravity we can energize turbulence, we can really create turbulence, that is a matter of debate that I am not going into. But simply when I am writing F, that is simply some external energy source. I am not saying anything. Okay, but this external energy source should be such that the energy is fed only to the largest eddies of the system. That means the force function should be such that this is only working for very large scales, or the scales near the macroscopic scales. Okay, the force is not acting, so I mean the energy is only injected from exterior to the system at macroscopic scale, and one way of saying that is to the largest eddies. Okay, now these largest eddies, okay, gets fragmented subsequently to smaller eddies, and this fragmentation is mostly due to the incompressibility of the fluid. A very easy explanation of this type of fragmentation can be easily understood by simply saying that, let's say you have a vortex like this, and of course as you are in a turbulent field, so there will be some discrepancy in the velocity at this point and this point. Okay, let's say at this point the velocity is greater. Okay, and once again, let's make it more simple. Okay, let's say the component of velocity in this direction, let's say this is the x direction, the component of velocity at this point in this direction is larger than that of the velocity of this point. So what happens, after some time this point will go farther, okay, and this point will not go farther. Okay, so so in some sense, so if you, I'm not, so maybe this is not the correct way of writing, but let's say if you have this type of velocity direction for this, so what happens after some times, let's say your vortex type of structure will be somehow distorted in one direction, because the fluid particle at which was previously at this point will be now much more farther, okay, than this the fluid particles at this point. Now the fluid particles at this point, let's say they come from here to here, and the fluid particles from this point to them, they have come from here to here, so thereby they have some distortion like that. Okay, so due to this discrepancy, you will see that in time you will have in one direction an elongation type of thing of the vortex, and after some times you can have a scission type of thing. That means the vortex, the structure would try to tear in the almost in the middle, okay, and thereby making two subsequent eddies, and where basically the incompressibility plays the role. So simply when, so once again I am just drawing the picture, this particle has a greater velocity, so it goes there and it maybe goes there, so now the structure is more like this, and then the structure with time is more like this. Okay, then what happens, you have to easily understand that since this is incompressible and we are just tracing of one one single vortex, so we are just concentrating on a given mass, okay, and we are just saying we are just following that with time how does that evolve, okay, and so for the given mass, if the density is constant, then of course it is very, very necessary that the effective volume should also be constant, otherwise this is not possible, right? So if this is the case, then you can simply say that after sometimes when the of course the volume is conserved almost, the volume conservation is still guaranteed, because there is an elongation and there is a compression in the perpendicular direction, right? So afterwards, when the elongation is too much, then in order to conserve the volume, of course the lateral dimension should be so small that it can actually have to tear at this point, and then you can see that you have two smaller eddies, okay, which are roughly, half of the size, okay. So that is simply the story of the fragmentation of the eddies. Now, when the larger eddies gets fragmented to the, they get fragmented to the smaller eddies, then what happens? The energy was first fed to the largest eddies. Now they are becoming smaller eddies. So energy is now effectively in the smaller eddies. So it is actually practically just by saying that the energy is cascading from the larger to the smaller eddies. Or if we just say that the size of the eddy is somehow equivalent to a length scale, okay, represents certain length scale, then we can say that the energy is cascading from larger to subsequent smaller length scale, okay, and this is known as the cascade of energy in turbulence, okay. So of course you understand that if the fluid is not incompressible, then this type of fragmentation is not guaranteed, and then this type of cascade is also not very easy to imagine, and that's one of the main problems in astrophysical turbulence, where most of the fluids are very much compressible. Now the point number 3 is that finally when the vortex size is so small, so there is a fragmentation process from the larger to the subsequent smaller eddies, and then this fragmentation reaches to such an extent that the vortex size is very small and it corresponds to the Reynolds number 1, okay. So all these things are just our phenomenological assumptions, okay. This is the phenomenological picture, so there is no hard and fast proof for that. We are just saying that we believe that the turbulent system should behave like that. So energy can cascade up to the extent where the Reynolds number is of the order of 1, and at this point which we call the corresponding length scale to be Kolmogorov scale, so that corresponds to Kolmogorov scale. Then we actually can say that starting from this scale, starting from this Reynolds, this vortex of this size with Kolmogorov scale, the energy is dissipated by the effect of viscosity. So no more fragmentation and cascade of energy takes place. Now between the forcing scale and the forcing scale, we can always say that this is the macroscopic scale, so we can simply designate this by the length capital L and the velocity capital V, okay, and the Kolmogorov scale, which is the dissipation scale, which we can designate by LD and VD, okay. Between these two scales, energy simply cascades from one scale to the subsequent smaller scale with a constant flux rate. So this is simply a very important assumption of the whole theory. So during the cascade process, the cascading is taking place in such a way that the energy flux rate is not depending on the scale chosen. So this is basically constant throughout the scales, okay. And so this process of cascading is simply independent of both the large scale geometry and the small scale dissipation mechanism, okay, because the cascade process is only characterized by a constant flux rate, and this constant flux rate does not really need any detailing, okay, of the large scale geometry and the small scale forcing. And so this that's why this process of cascade simply gives us a concept of universality or universal behavior of turbulence, because it is roughly it is saying that the energy is injected at this scale. So this is the largest scale and or called the forcing scale or integral scale, and energy is dissipated here. This is the Kolmogorov scale where the energy dissipation is taking place between these. And actually, although for picture, for the for the communication purpose, it is drawn like that, but between these two simply does not mean that just starting from this one and reaching to the Kolmogorov scale. When we are talking about simply the cascading with a very with a scale independent flux rate, energy flux rate, then we simply talk about a range of scales which are in between these two scales, but also very far from both the scales. So in a sense this should be like here. Okay, maybe much more practical is like this. This could be the range of scales in which the proper cascading takes place with a scale independent energy rate. Okay. And so it is also true that these things are very subtle. Okay, these things are very subtle, and this range and that's why, because this range is also far from both this scale and this scale, this range is not really affected by any of the two, and therefore this range is known as the inertial range, and this range is universal for any turbulent system, because it is, let's say your turbulence is in a spherical jar or in a cubical box. Okay, for both this is the same. Or you have a turbulence in tap water, or your turbulence is in a salt water. Okay, so it's the same. Okay, let's say you have turbulence in glycerin or in oil. Okay, well, the viscosity is different, but this cascading process is universal, because this does not also care about the viscosity, nature of the viscosity. Now at this point we have to take care of this, that although we are saying that the inertial range, which is, so if I can write here, I will try. So this is known as inertial range. Okay, so here in this inertial range you can simply see that the bigger eddies or the larger eddies, they are fragmented into subsequent smaller eddies to such an extent that the eddies are they reach to the scale of smallest eddies, and this is the so-called Kolmogorov scale or the energy dissipation scale. Now at this point, we should remember that although we are saying that inertial range is very far from both this range, when we will do some phenomenological treatment, we will actually say that the energy is injected to the system, let's say at some rate. Okay, that the energy injection rate to the system is actually equal to the energy cascade rate, and that is actually equal to the viscous dissipation rate, and that is the necessity of having a stationary regime in turbulence. Okay, that was one of the fundamental hypotheses of Kolmogorov. Okay, now we can do something here. At this point we will do something which is heuristic. That means it does not have any proper analytical rigorous mathematical background, but we will do some simplistic estimate just by using the order analysis, and of course it's a very crude treatment. Okay, so maybe you can have some complaint about the mathematical rigor of this part, but well, this is how that historically or traditionally the turbulence field was studied at the very outset. Okay, so we starting from we have postulated several points, and based on those points we will now trying to construct some some quantitative results. So the first one, according to our definition, this is the Reynolds number at the Kolmogorov scale, which should be of the order of unity. So LD times VD by nu, so that is the Reynolds number definition in case you have forgotten. So Reynolds number definition for a length scale is the velocity of that scale times this length scale by the coefficient of viscosity. So for our case, we simply say the coefficient of viscosity is not a function of length scale. Okay, this is roughly true. Okay, so if this is true, then LD times VD will be of the order of nu. Okay, once again, we know that the macroscopic Reynolds number, which is capital L capital V by nu, should be very greater than 1. So LV should be very greater than nu. Now energy cascade rate epsilon, that is something which should be dimensionally, I mean this is the thing which is actually, according to our assumption, should be scale independent, and dimensionally it is nothing but the energy, the density of energy per unit time. Okay, so that's why we can write, so here in our case, so for incompressible turbulence, traditionally we just say that there is density, of course, so rho L is there, but rho is constant, so we are just normalized everything in the at rho is equal to 1. Okay, and so according to that normalization, epsilon will simply be VL square by TL. Okay, tau L. Okay, now this tau L is the time required effectively for the fragmentation of an eddy of length scale L, right? And this is, again, this is roughly is nothing but VL by L. Okay, so if that is the only possible time scale we can, not VL by L, L by VL, that is the only possible time scale we can make. Okay, so then we can simply replace this TL tau L by L by VL, and you have epsilon is equal, of course, of the order of VL cube by L. Okay, now we have to have stationarity. That means that if you just write the Navier-Stokes equation and you write the energy equation, kinetic energy evolution equation from Navier-Stokes equation, in case you are not clear at this point, let's say we take the dot product of by velocity to both sides, and then you simply do the evolution equation for kinetic energy. You will see that when if you just if you assume a stationary state, okay, then this is 0, and then the other two parts, so there will be actually finally there will be a balance between, so between this nonlinear part, so the balance between this nonlinear part, and this this dissipative part and the forcing part. This part actually does not play any role, because if you just understand that V dot nabla P, V dot gradient of P, so for incompressible case V is divergence-less, so this will be simply P divergence of PV, this one. Okay, and this one, so we are now trying to see that del T of integration half V square actually d tau, so this one will be something of nature divergence. So by Gauss's divergence theorem you can forget that, but one part of this will remain and these parts will be remaining. So there will be a balancing between this nonlinear term and this dissipation term and this forcing term. So at very large scale the forcing term remains, is the part which contributes. In the intermediate part this one contributes, and in the very small scale this one contributes. Okay, so now the thing is that of course the forcing specifically is given at the very large scale, so it is always, so once this is injected you have this. So in the very in the intermediate scale this part is balanced by this one, and in the small scale simply this part is balanced by this one. That's it. Okay, so when this part is balanced by this part, then we can simply say that the forcing, that the energy injection rate should be exactly equal to the energy flux rate by the nonlinear cascade. Okay, once again, if this part simply counterbalances this part in the stationary regime, of course, then you can say that the energy dissipated by this dissipation term will be exactly equal to the energy injected. So all these three actually should have, if you think, should have the same flux rate. Okay, so the energy injection flux rate should be equal to the cascade energy flux rate, should be equal to the energy dissipation rate. Okay, that means, or the flux or the dissipated rate of the dissipated energy flux. Okay, so for the first one, so for the stationarity, we first have this cascade rate, that means the VL cube by L, which is the epsilon, should be almost of the same to VD cube by LD, that is the energy dissipation rate. Okay, once again energy flux rate, the density of energy per unit time. Yeah. So, and then from this one you can simply say that just a minute. So if you just see, this is the B, number B. So this one you can say that since this is something which is not depending on L, okay, so then you can say that VL cube will be of the same order of L, so VL will be proportional to L to the power 1 by 3. And again, using A and C, so who are A and C? A is this one and C is this one. Okay, using A and C, so what you have to do, you have to simply write epsilon, which is from your definition VD cube by LD, and then this one can be simply written in terms of this. Okay, so where you just get rid of VD, okay, and you have epsilon will be nu cube by LD to the power 4. Okay, and then you can simply write LD will be of the order of eta cube, nu cube by epsilon to the power 1 by 4. So that's a very important piece of result. And again, VD, which is of course like this one, VD is also proportional to LD to the power 1 by 3rd. So VD can actually be equal to nu times epsilon by nu cube 1 to the power 4, right? Simply. Okay. So this one can be easily explained, because once you have LD, just you use this one. Okay, VD is nothing but nu by LD. Okay, so nu by LD gives you VD is of the order of epsilon nu to the power 1 by 4. Okay, so just you can check, you can just multiply these two and you will have nu. Okay, so that is the estimation of the dissipative length scale or the Kolmogorov scale and the corresponding velocity in terms of the viscosity and the energy flux rate. Okay, now which is also equal to the viscous rate. Now if we just define the macroscopic Reynolds number to be capital V times capital L by nu, and for stationarity, then we again need the energy injection rate should be equal to the energy cascade rate and should be equal to the energy dissipation rate. We simply can say that L by small l d will be of the same order as V by Vd whole cube. That you can simply compare these two and you can have this one. Okay. And finally, when you do L by LD, then this is nothing but V cube by epsilon. Okay, that's simply their definition. So L will be V cube by epsilon from this equation, and LD will be from this equation eta 3 nu to the power 3 by 4 by epsilon to the power 1 by 4. And if you do this corresponding manipulations, you will have L by LD will be VL by nu whole to the power 3 by 4. And what is VL by nu is nothing but the macroscopic Reynolds number. So L by LD will be of the order of macroscopic Reynolds to the power 3 by 4. And the corresponding ratio for the velocities, that means the macroscopic to dissipative length scale velocity, or rather forcing scale velocity to Kolmogorov scale velocity, will be simply 1/3 of this thing, which will be Re to the power 1 by 4. So now just let's take one simple example, very typical example. For laboratory experiment, we have seen that for water, for example, for tap water, the turbulence takes place at a macroscopic Reynolds number 10 to the power 4. So that means that the macroscopic scale to the microscopic scale is of the order of 10 to the power 3. So there are 1000 length scales. Okay, or at least, I mean, of course, saying like this is a bit confusing. What we can say that the forcing length scale is 1000 times greater than the Kolmogorov length scale. Okay, but the velocity of the forcing scale is just 10 times greater than the dissipative velocity scale. Okay. Now, a large macroscopic Reynolds number therefore corresponds to a considerable separation between the forcing and the viscous scales. Okay, so if Reynolds number is larger, then L by LD will be larger, and that means that the L to small ld distance will be larger. So the separation between the forcing and the viscous scales will be larger, and that creates a larger inertial range. Finally, we have to remember that all the above arguments are heuristic and cannot be derived, not known till date at least, from the first principle directly. However, I mean, how can we check that? So we have made some hypothesis, and depending on that hypothesis, we have given at least some estimations, quantitative estimations. Okay, and we can simply verify those in natural systems, and if that works, then we are happy. Okay, and that is actually systematically done in terms of the quantity, which is energy spectra, which is E as a function of key. Okay, so because, I mean, practically speaking, that you can measure my macroscopic velocity, macroscopic length scale, but how can you measure mesoscopic, I mean, between the microscopic and macroscopic, I mean, between the forcing and the dissipative scale velocities and length scales? This is not very easy. So therefore, what we will do in general, we calculate something which is much more traditional to calculate, is the energy power spectra. Okay, and it is EK. What that is, so in order to understand that, we have to go to this point that since Navier-Stokes equation is nonlinear in nature, and as the turbulence motion is nonlinear in nature, then we cannot neglect the nonlinear term. Okay, and if you do the Fourier transform in Navier-Stokes equation, then simply you can understand that the nonlinear terms in Navier-Stokes equation will involve more than one wave modes. So if the term is linear, then if you just do the Fourier transform of the term, so one quantity at some space point x will correspond to some other wave mode k in Fourier space. But if the quantity is nonlinear, if the term is nonlinear, then any term corresponding to a single point in real space corresponds to more than one wave modes, and therefore we talk about the triads. Okay, so that is a bit well, okay, maybe if you are interested you can see any standard textbooks of turbulence. So actually it involves so the nonlinear term of Navier-Stokes equation involves three wave modes P, Q and K, such that P plus Q is equal to K. Okay, so there will be a triadic relationship. I mean, they should follow the rule of triangle addition. Okay, so this type of thing. So but here, however, one can be somehow, so we see that one point description in real space is not one point description in Fourier space. So one can say, okay, now we can actually be interested in the one point description in the Fourier space, right? So one can be interested to know how the properties of turbulence changes as a function of wave mode K in a Fourier space. That means a single wave mode. Okay, so I have to write that a single wave mode K in Fourier space, and that then says that, okay, so if we are now concentrating on a single wave mode K in Fourier space, that means it cannot be given by a single point description in direct space. So then we actually have to think of two-point correlation function like this, and this is exactly supported by Taylor's work of 1935, which says that we have to be interested in two-point correlation functions, because he also thought that the main, in order to know the main mystery of turbulence, we rather to be localized in direct space, we have to be localized in spectral space, and therefore we have to consider more than one point correlation functions, because if you are now considering the Fourier transform of the correlation functions, that will give you something corresponding to only one single wave mode. Okay, so but what is this epsilon Ek? So Ek is the energy density in this is the energy density in spectral space, or you can say that so this is, so I don't know whether I have written this or not. So in a sense, if for incompressible case, when rho is simply normalized to unity, so v square is the, so half v square averaged is the average energy of the kinetic energy for this system, and Ek is such that, so I am just talking about homogeneous and isotropic turbulence, that's why we are simply taking K as scalar, so 0 to infinity. So this is the definition of Ek. Okay, and now we try to check the K dependence of Ek. So before that, let me just designate KL as 1 by capital L, which is the wave number corresponding to the largest eddies. So that means that is the smallest possible wave number in our system, and KD is 1 by LD, that is the wave number for the smallest eddies, so that is the largest possible wave number for our system. Okay, so according to Kolmogorov's assumption, Ek can be expressed only in terms of epsilon and K. So that actually comes also from his universality hypothesis. Okay, but here you just learn this as information. So if you do that, okay, I have written the definition in any case. So the definition is simply giving that half of average v square is equal to integration Ek dk, and this v square then will be dimensionally equivalent to Ek times k. So Ek should have a dimension L cube t to the power minus 2. Okay, and if you simply follow normal dimension analysis and you say that Ek is only a function of epsilon and k, then just by doing dimension analysis you will say that the only possibility is that Ek should be, should scale as epsilon to the power 2/3 times k to the power minus 5/3, and epsilon is something which is independent of scale, and so it is also independent of k. Okay, and then finally Kolmogorov also said that there should be a constant of proportionality which nearly makes them equal, and this is known as the constant of Kolmogorov. Okay, now this constant of Kolmogorov can be different from different turbulent system. Okay, so here you see that the E of k basically varies as k to the power minus 5/3 for a given turbulent system, and this is nothing but the Kolmogorov's minus 5/3 law. So what you have to do, so if you now understand what Ek is nothing but the Fourier transform of the 2-point correlation functions. So you have to calculate the 2-point correlation functions for a system, and you have to take the Fourier transform, then you have to get, you will get Ek, and then you just plot log Ek versus log k, and you will find that which type of graph it should give, and you will see that this is the injection, this is the dissipation. Between these two, this is the cascade part where you have a power law which varies as k to the power minus 5/3. Okay, now you see that this relation is so universally true, and that it can be actually valid for most of the systems. So here I am just saying that I have taken this picture from one of the books, and you can see that so they are consisting of different different systems. One is seawater, one is like the normal tap water, one is the atmosphere. So atmosphere is also can be considered to be incompressible. Okay, so and actually that's why Richardson's original image was so good that it worked for atmosphere. Okay, so here you see that although their dissipation, the point where they starts dissipating are different, but they all of them have some common range with this type of power law. And actually the fabulous thing is that when you calculate the slope, this is minus 5/3. Okay, so this minus 5/3 spectrum is a signature of universality of turbulence. Okay, so now in a different system, for example, if the fluid is a plasma or something, then this type of universality is also existing or not. That's exactly what scientists always try to find out. Okay, so we have seen that we are finally using some very crude phenomenological considerations. We have given some at least a functional dependence of Ek, okay, with the wave number. But now coming back to this so-called the analytics, okay, can we just now, our thing is that can we relate at least this? So up to this point I said that we cannot do anything. So for example, when up to this point we said that all these above arguments are heuristic and it is not possible to derive them from first principle, but at least when using those things, finally we arrived at this result, which is quite fantastic. Okay, now the question is, can we relate this to something much more analytically sound? So for that we have to see the development of analytical approaches after that. So as I said that after Taylor's suggestion in 1935, von Karman and Howard, they derived in 1938 the evolution equation for the 2-point velocity correlation function. But that was not simply, that was also an exact relation, but it was not simply a very good constraint, just just using 2-point correlation function or something like that to the energy correlation. There was always a del T of this the correlators Rij. Okay, now Kolmogorov derived for stationary and homogeneous and isotropic turbulence. Stationary means this del T term was 0, and he then derived that the longitudinal velocity, how to say that, third order structure functions of the longitudinal velocities. Okay, so what is the third order structure function? That means if you take the increments of 2 points, that means the velocity increments delta VL, that is nothing but the V of x plus L minus V of x, of course at a given time. Okay, so if you take this and then you take the this component parallel, that means if you take some length scale, okay, or some distance, then you take the projection of this vector with respect to, along this direction, then you have delta VL parallel, and then you take the cube of this. Okay, once you take this cube of this, then you can calculate this, all the couple of points which are separated from each other by a length L. Okay, and then you take the average. Here you are simply doing the space average, okay, for practical purpose, although it should be ensemble average in general. And then you just plot this. So you just plot this with the modulus of L vector, which is L, and you will see that the slope will be minus 4 by 5 times epsilon. So here, from here you are actually also calculating epsilon. Okay, and if you simply see that this one, now this one, what is this? This, if you say that this delta V L cube is nothing but my roughly VL cube is a turbulent velocity cube by L, okay, then that is proportional to, that is of the order of epsilon. So that's exactly what we found here. At this point. Okay, so here we can see that this equation, which is known as the 4/5 law of Kolmogorov, the previous one was the minus 5/3 law, this is called the 4/5 law of Kolmogorov. Or the exact relation of turbulence. Okay, and we saw that this equation also gives the indication that we can derive minus k to the power minus 5/3 law from this, because once you have this V cube by L is something scale independent, then actually you can simply write, I can do that, if you have V cube by L, which is of the order of epsilon, which is scale independent, then you can say my V will be something, so you know that V square is of the order of EKK, so you can simply say that my V cube will be EKK whole to the 3 by 2, and then L can you can write as K minus 1 epsilon, and now I leave it to you to simplify, and you will see that you will retrieve EK K to the minus 5/3. Okay, and not only that, epsilon to the power 2/3 will also come. Okay, so you see that this result, this k to the power minus 5/3 result, can actually also be obtained from exact relation as well. Okay, so in the next lecture I will discuss the Reynolds decomposition, and then I will shortly introduce turbulent viscosity, and because that is something very interesting for accretion disks, and then I will talk very qualitatively the a little bit of plasma turbulence, of course, and finally I will sum up by saying something qualitative for the turbulence in astrophysical contexts. Okay, so but of course not in this week. That will be the program for the first lecture of next week. Okay, thank you very much.